compared to cosmological scales of the large scale, probed by the large scale structure. You get very early assembly of halos. That's a good thing. You get smaller number of satellite galaxies simply because things merge early on. The smaller things would have already merged before they even collapse to become satellite galaxies. That's a good thing. You get deeper voids, not larger. That's actually also a good thing. You get a varying baryon fraction in halos, and that's a good thing because there are strong indications that the fraction of baryons in halos is smaller for smaller halos and approaches the global value for clusters. So that's, you get this naturally here. It helps in generating pure disks. Pure disks, no one so far has managed to generate the pure disk without any bulge, like what Kormandi wanted in the local universe. This is really a challenge. Okay, the fire simulations by Hopkins, they generate disks without a bulge, but the problem is these are thick, and we know that. And okay, this is a problem. They can give you more cuspy halos. I don't want to focus on any of these. This is just to show you the fraction of baryons. What you expect is this. What you observe is this. This is a function of the halo mass, if you want, circular velocity. Now I want to talk about the test of the force, of the dark force, using galactic satellites. So we have also satellites in our galaxy, and why is this a test?
So
yes?
Just to kind of orient myself, this R sub S, this Dukawa, what is the order of magnitude of R?
1 megaparsec.
1 megaparsec. So we are big.
It's real big, yeah, it's a large scale force.
And you said it expands with the expansion.
It's co-moving.
It's co-moving.
But if it's related to a mass, why would it?
It's not related to a mass.
Oh,
That's right. If it was, then it would be called to be a mass.
It's not related to a mass. That's why the model there is actually you introduce a field and you do it. Yeah. It's related to a mass. It's just doesn't work. Okay, so I will going to show you some movies which were made a long time ago, and I will connect them to something new. So if you have a satellite, this one, say it's a Sagittarius one, moving into the potential of the Milky Way. The dark matter is the blue, the stars are the, I actually can't remember anymore. The stars are in the middle. You will see very soon what is what. So let me run this. Hopefully it will run. Is it running? Ah, good. So you see that actually the star is at the center of the halo, of the Sagittarius satellite, and the rest, the red is the stars, and the blue is the dark matter, and you see these characteristic streams. They are sort of symmetric, you know, they follow the trajectory of the satellite. Okay, now let's do something else. Let's introduce an additional force in the dark sector, this Yukawa potential, which acts only on the dark matter. Now I'm going to start causing segregation between the dark matter and the stars. Okay, so that's why it's breaking the equilibrium principle, because the acceleration depends on what the satellite is made of. Let's do this. And this is a test which was originally proposed by Free. No, another one. Sorry, I think so. I think I spelled the name. I'm so embarrassed. I met the guy a few months ago. So this test is he actually referred to the RS, the old model where you have a mass. But the test is the following. You will see. So if you have this force, and the dark matter will continue, but the stars, the stellar stream will not be symmetric. Okay? Because it's still bound, the stars are still bound to the dark matter, but the dark matter is the one which is causing more acceleration, has more acceleration than the stars, and you get something which is not symmetric. This is a very important test. Note here that I put beta equals 0.1. This is not consistent with the Swampland conjecture, with the weak gravity conjecture of Vafa. So let's see what happens when I take beta equals 1. The magnitude of the force, the force is large actually. Is it going to match the observations? Let me see. So here you see very quickly the stars and the dark matter separated very completely. And now two components. We have the challenge is whether whatever remains from the stellar component is actually bound. This could be arranged, of course. So we got something which is bound. We got something which matches the Sagittarius. And you cannot rule out large values of beta using the Sagittarius stream, for example.
What about the bullet cluster? You cannot rule this.
Bullet you cannot rule, because
But in
it
the
works in
bullet
dark
cluster,
matter.
You see the X-ray gas and the dark matter in the right place.
You see the X-ray gas and dark matter, it's true. The galaxies are far away a little bit. But it's very hard to, because you can put constraints, but I'm not sure I want to answer now because I don't remember. There is some subtlety there. I can't remember. It's a good point. I just can't remember. Sorry. So now, let me continue with what happens now with the observations. So that was about Sagittarius, because Sagittarius fits, and actually the Sagittarius is very close to the galactic center. It's about 16 kiloparsecs, so it's the tidal field is very important there, so you inflate the velocity dispersion by hand. Now, there is a hammer which landed upon us, and this is by Francois Amer. I think that's how he pronounces his name in French. He made a very interesting proposition here in his group. If you look at all galaxies, satellite galaxies in the Milky Way, he claims you can get away without dark matter at all. And his argument is that if you plot, so this is here, this here, if you want, this is what you would get, the claimed amount of dark matter. MDM, if you do genes analysis. And he says, this is correlated or anti-correlated with the distance from the center of the galaxy. And he's asking, why then should that be? It shouldn't be. Unless the reason that you have higher velocity dispersion than what you, is not dark matter, but rather sort of tidal squeezing or tidal effects which are affecting the dynamics of the satellite galaxies. And what he plots here is the acceleration which it's the velocity dispersion which you expect if you have some sort of an impulse approximation acting on these galaxies when they are moving in the galactic center. So versus, oh, I made a miss, sorry. Versus the observations. And he says that you actually get a very good correlation. It's very hard to dismiss this. You have to go into the data and his analysis, their analysis, the level of detail to dismiss it, okay? So, okay. So for Sagittarius, this really happens, definitely. This is the velocity dispersion which you get for the Sagittarius. Is the line of sight one? Yes. This one is the line of sight, and you see an inflation or an increase in the velocity dispersion when the satellite is near the galactic center. But the Sagittarius special case, it's just at 16 kiloparsec from the center. So I don't know the claim of if that his claim is correct or not, but it's worth investigating, and I would like to do that in the next few months. This is, I will skip this. Now, this is actually the final point. I hope I can do it in 10 minutes, and then I will really finish in 40 minutes. I won't break my promise. I was very excited about these two galaxies, or whenever the first one which appeared. A galaxy lacking dark matter. Oh, that's fantastic. It's in a group. It's at the distance of, what's the distance? 20 megaparsec from us. This is an ultra-diffuse galaxy. And these guys say that there is no evidence for dark matter in it because the velocity dispersion is very small. And I said, fantastic. Now we have, this is a smoking gun for the model I'm trying to advocate. However, so their measurements of the velocity dispersion was based on globular clusters, 10 globular clusters, which gave this. So these globular clusters are peculiar in this galaxy. I will get to that later, why they are peculiar. But before that, we want to be, if you look at the stellar mass of the galaxy, which is about 10 to the 8, more than 10 to the 8 solar masses in the stellar component, and you look at what you expect in other galaxies in terms of the content of the dark matter, then it's here. It's supposed to be 10 to the 11. But their analysis of the Laplace dispersion gave you something here. So there is very little room for dark matter in their analysis. Actually, this is not the first time we hear of claims of no dark matter in galaxies. So let me demystify the whole thing of a galaxy of no dark matter. For example, there has been a claim a long time ago that ordinary elliptical galaxies don't have dark matter if you measure the kinematics from planetary nebula. Planetary nebula get far out. But then again, that claim, the dark matter was found by these guys who argued that it's a matter of how the planetary nebulae move inside the galaxy. So we're not, in fact, if you look at this paper, from Sloan galaxies, then these guys, what they find is the mass, the virial mass, basically the total mass to the stellar mass of many of the galaxies don't actually get to the global value. There seems to be no dark matter here. But of course, you know, these are elliptical galaxies. This is not this galaxy which rotates, and you can actually make the measurements. You don't have the measurements everywhere, so everything here that doesn't imply that there is no dark matter. Okay, there is an issue with the distance of that galaxy. I will skip that. However, I don't want to skip the fact that the global cluster of this galaxy, this, let me call it the F2, are peculiar. They are